By the late 19th century, physics stood at a moment of extraordinary confidence. For more than 200 years, the laws established by Isaac Newton had explained motion, force, and mechanics with astonishing accuracy. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single elegant framework. Thermodynamics had clarified the behavior of heat and energy. To many leading scientists of the time, the universe appeared fundamentally understood. The grand structure of nature seemed complete, solid, and mathematically beautiful. What remained, they believed, were only small refinements, minor measurements, and technical details to be polished by future generations. This belief was not naive optimism. It was grounded in real success. Classical physics had predicted planetary motion with precision, explained tides and pendulums, powered steam engines, and enabled the Industrial Revolution. Telegraphs, electric lighting, and mechanical engineering all rested on well-tested physical laws. University textbooks confidently presented physics as a finished monument of human knowledge. Some physicists even warned students that there was little left to discover, advising them to seek careers elsewhere if they desired originality. Yet beneath this surface of certainty, subtle cracks had begun to appear. Certain experimental results stubbornly refused to fit within the established theories. At first, these discrepancies seemed small and easily dismissible, but as measurements grew more precise, the cracks widened. What had once appeared as minor anomalies began to signal something deeper. The classical picture of nature was incomplete. One of the most troubling problems involved heat and radiation. When objects are heated, they emit electromagnetic radiation. This phenomenon is visible in everyday life. A piece of metal glows red when heated, then white as it becomes hotter. Classical physics attempted to explain this behavior using known laws of electromagnetism and thermodynamics. Early theories worked reasonably well at low frequencies, but failed dramatically at high ones. According to classical predictions, a heated object should emit infinite energy at short wavelengths, an absurd and impossible result that came to be known as the ultraviolet catastrophe. This was not merely a theoretical inconvenience. Experimental measurements were clear and repeatable. Laboratories across Europe produced consistent data that directly contradicted classical expectations. The equations were elegant, but nature did not obey them. The more physicists tried to fix the problem using existing ideas, the more tangled the mathematics became. The failure was fundamental, not technical. At the same time, other mysteries challenged classical thinking. The behavior of atoms, long considered indivisible and structureless, began to raise questions. Spectral lines emitted by elements appeared at precise frequencies that classical models could not predict. Energy exchanges at microscopic scales seemed oddly constrained, as if nature followed rules unknown to existing theory. Even the stability of atoms could not be satisfactorily explained. According to classical electrodynamics, electrons orbiting a nucleus should continuously lose energy and collapse inward, yet matter was clearly stable. Despite these issues, most physicists resisted radical change. Classical physics had earned its authority through centuries of success. The prevailing mindset favored adjustment rather than transformation. Scientists searched for hidden variables, improved measurements, or mathematical tricks that might preserve the established framework. The idea that the foundations themselves might be flawed was deeply uncomfortable. This intellectual atmosphere is essential to understanding the significance of what followed. The crisis of late 19th century physics was not dramatic or sudden. It unfolded quietly in academic journals, laboratory reports, and conference discussions. There were no public declarations of failure, no collapse of institutions. Instead, there was a growing sense of unease among those working closest to the data. The universe was behaving in ways that theory could not fully explain. Into this environment stepped Max Planck, a physicist who was, in many ways, an unlikely revolutionary. Planck deeply respected classical physics and admired its logical structure. He was not seeking to overthrow existing ideas. In fact, he believed strongly in determinism and order, values that aligned closely with classical thought. His goal was not to invent a new theory of nature, but to solve a specific problem related to thermal radiation. Planck approached the radiation problem with mathematical discipline and philosophical caution. He analyzed experimental data with extreme care, attempting to derive a formula that matched observation. When classical methods failed, he faced a difficult choice: accept that nature behaved in a fundamentally unfamiliar way, or abandon the hope of a solution altogether. Reluctantly, he chose the former. The scientific crisis of the era forced Planck to take a step that would have been unthinkable only decades earlier. To make the equations work, he proposed that energy could be absorbed or emitted only in discrete amounts. This assumption directly contradicted classical ideas, which treated energy as a continuous quantity. At first, Planck regarded this step as a mathematical trick rather than a physical truth. He believed it was a temporary measure, a compromise forced by stubborn data. Yet this compromise revealed something profound. The failure of classical physics was not due to incomplete measurements or flawed experiments, but to incorrect assumptions about nature itself. The continuous, smooth universe imagined by 19th-century physics did not exist at the smallest scales. Instead, reality operated in steps, jumps, and quanta. The importance of this realization cannot be overstated. It marked the end of an era in which the universe was viewed as a perfectly predictable machine. The crisis that classical physics faced was not a sign of weakness, but of transition. Like the moment when Newtonian mechanics replaced Aristotelian ideas, the breakdown of classical theory signaled the birth of a deeper understanding. What makes this moment especially remarkable is how quietly it occurred. There was no dramatic rejection of classical physics, no sudden collapse of its authority. Classical laws continued to work brilliantly for large-scale systems, and they still do today. But at the microscopic level, a new description was required. The crisis revealed the limits of certainty and the boundaries of human intuition. In hindsight, the confidence of 19th-century physicists appears both justified and incomplete. They had mapped much of the visible universe, but the invisible world of atoms and energy remained unexplored territory. The crisis they encountered was not a failure of science, but evidence of its progress. Only when theories become precise enough do their limitations become visible. This period of uncertainty created the conditions necessary for revolution. Without the unresolved contradictions of radiation, atomic stability, and energy distribution, there would have been no reason to question classical assumptions. The silent tension between theory and experiment became the pressure that reshaped physics forever. By the time the 20th century began, the old certainty was gone. In its place stood a new awareness. Nature was stranger, more subtle, and less predictable than previously imagined. The crisis of classical physics did not destroy the field, it transformed it. It opened the door to quantum theory, relativity, and a radically new understanding of reality. This moment, often overlooked in popular narratives, was the true beginning of modern physics. Before equations changed and constants were named, before quantum mechanics was formalized, there was a quiet realization that the universe did not obey the rules humans expected it to follow. That realization marked the end of classical certainty and the beginning of a deeper, more mysterious view of nature, one that Max Planck would soon help define. As the 19th century drew to a close, the growing tension between theory and experiment could no longer be ignored. Physics, once admired for its certainty, was now marked by unanswered questions that refused to disappear. These questions were not raised by outsiders or critics, but by the most precise experiments conducted by physicists themselves. Every improvement in measurement sharpened the contradictions. Nature, it seemed, was quietly but firmly resisting the classical description imposed upon it. The discomfort this caused within the scientific community was profound. Classical physics was not merely a collection of equations, it was a world view. It promised predictability, continuity, and order. According to its principles, if one knew the present state of a system with sufficient accuracy, its future could be calculated exactly. This belief extended beyond science into philosophy, reinforcing the idea that the universe was a perfectly functioning machine. The emerging anomalies threatened not only specific theories, but the intellectual foundation upon which centuries of scientific confidence had been built. One of the most unsettling aspects of the crisis was that it emerged from phenomena that should have been simple. Thermal radiation, for example, involved everyday objects and well-understood principles. Heat, energy, and light were familiar concepts. The expectation was that such phenomena would be easily explained by existing laws. Instead, they became the source of deep confusion. The fact that classical equations produced nonsensical results, such as infinite energy emissions, suggested that something fundamental had gone wrong. Physicists responded in different ways. Some attempted to modify existing theories slightly, hoping that small corrections would restore agreement with experiment. Others questioned whether experimental techniques were flawed, suspecting hidden errors or limitations in instruments. A few proposed speculative ideas, but lacked mathematical support. None of these approaches resolved the contradictions. The persistence of the problem made it increasingly clear that classical physics was reaching the limits of its explanatory power. This realization unfolded slowly and reluctantly. Science rarely abandons successful ideas without resistance, and for good reason. Classical physics had proven its value countless times. Engineers relied on it, astronomers trusted it, and educators taught it with confidence. Letting go of such a powerful framework felt dangerous. Many feared that abandoning continuity and determinism would lead to chaos rather than clarity. The crisis also revealed a deeper philosophical challenge. Classical physics assumed that nature was fundamentally intuitive, that its behavior could be understood through smooth curves, continuous motion, and cause, and effect relationships that mirrored human experience. The experimental anomalies suggested otherwise. At microscopic scales, nature behaved in ways that defied common sense. Energy appeared to move in steps rather than flows, and matter displayed unexpected stability that classical theory could not justify. This growing awareness forced physicists to confront an uncomfortable possibility. Human intuition, shaped by everyday experience, might be an unreliable guide to the true workings of the universe. The laws governing the visible world might not apply to the invisible one. Such an idea required humility, a recognition that centuries of success did not guarantee completeness. Universities and research institutions became centers of quiet debate. Scientific journals filled with increasingly technical papers attempting to address the anomalies. Conferences featured cautious discussions rather than bold declarations. There was no single moment when physicists collectively admitted defeat. Instead, there was a gradual shift in tone, from confidence to curiosity, from certainty to questioning. The crisis was not limited to radiation alone. Atomic theory, still evolving, raised serious concerns. The structure of atoms remained mysterious, and classical models failed to explain why atoms emitted light at specific frequencies. The regularity of spectral lines suggested hidden rules governing energy transitions. These rules were precise and universal, yet invisible to classical mechanics. Matter itself appeared to follow an internal logic that classical physics could not decode. Despite these challenges, classical physics continued to function remarkably well in everyday applications. Bridges stood, engines ran, and planets followed predictable paths. This dual reality created confusion. How could a theory be both extraordinarily successful and fundamentally flawed? The answer lay in scale. Classical physics worked where human senses operated, but faltered where nature became granular and discrete. This realization marked a turning point in scientific thinking. Instead of seeking a single, all-encompassing description of reality, physicists began to accept that different domains might require different rules. The idea that a theory could be approximately true rather than absolutely true gained acceptance. This shift represented a profound change in how science understood itself. The crisis of classical physics thus served a critical function. It exposed the limitations of even the most successful theories and demonstrated that progress often arises from failure rather than triumph. Without the stubborn refusal of experimental data to conform, there would have been no motivation to explore new ideas. The discomfort generated by contradiction became the engine of discovery. As the 20th century approached, the scientific atmosphere grew increasingly open to unconventional thinking. Younger physicists, less invested in established frameworks, began to question long-held assumptions. Mathematical rigor remained essential, but philosophical flexibility increased. The stage was set for a transformation that would redefine physics at its core. This transformation did not occur overnight. It emerged from careful reasoning, reluctant acceptance, and a willingness to follow evidence wherever it led. The crisis had stripped physics of its illusion of completeness and replaced it with a deeper sense of mystery. Nature was no longer a perfectly transparent system waiting to be decoded, but a layered reality revealing itself only under precise and sometimes uncomfortable scrutiny. In retrospect, the crisis at the end of the 19th century appears not as a failure, but as a necessary passage. It marked the moment when physics outgrew its classical framework and prepared to enter a new era. The questions that could not be answered forced scientists to rethink what questions were worth asking. The anomalies that once seemed like minor inconveniences became signposts pointing toward a richer understanding of the universe. This quiet intellectual upheaval laid the groundwork for everything that followed. Quantum theory, relativity, and modern physics did not arise from bold rebellion, but from careful attention to nature's refusal to behave as expected. The silent tension between theory and reality reshaped scientific thought more powerfully than any dramatic proclamation ever could. By confronting the limits of classical physics, scientists learned that certainty is not the goal of science, but understanding. The crisis taught them that the universe does not owe humanity simplicity or comfort. It follows its own rules, waiting patiently for minds willing to question, adapt, and listen. In this sense, The breakdown of classical physics was not the end of an era, but the beginning of a deeper conversation between humanity and nature, one that continues to unfold to this day. At the turn of the 20th century, the idea that energy could be divided into discrete portions was not just unfamiliar, it was deeply unsettling. For generations, physicists had treated energy as a smooth and continuous quantity, capable of changing by any amount, no matter how small. This assumption felt natural because it aligned perfectly with everyday experience. A swinging pendulum slows gradually, heat spreads smoothly through metal, and light appears as a continuous wave. There was no obvious reason to imagine that energy behaved differently at microscopic scales. Max Planck himself shared this belief. He was not a radical thinker by temperament, nor was he inclined towards speculative ideas. He valued order, determinism, and mathematical consistency. His scientific philosophy was shaped by classical traditions, and he believed that the laws of physics reflected an objective and rational structure of nature. When Planck began studying thermal radiation, his goal was to preserve classical physics, not replace it. The problem he faced was deceptively simple. Experimental data describing how heated objects emit radiation were precise and reliable, yet no existing theory could reproduce the observed distribution of energy across different wavelengths. Classical approaches either matched the data at low frequencies or at high frequencies, but never both at the same time. Attempts to blend these approaches failed. The equations stubbornly diverged from reality. Planck approached the problem with meticulous care. He analyzed experimental results line by line, seeking a mathematical expression that would fit the data exactly. For years, he resisted abandoning classical assumptions. Instead, he explored every possible variation within the established framework. The difficulty was not a lack of mathematical skill, but a conceptual barrier. The classical view of energy simply could not accommodate the experimental facts. Eventually, Planck reached a point where no classical solution remained viable. Faced with this impasse, he made a decision that would later be described as an act of desperation. He proposed that energy exchange between matter and radiation occurs only in discrete units proportional to the frequency of radiation. These units were not arbitrary, they followed a precise mathematical relationship. Energy, according to this idea, could only be emitted or absorbed in fixed packets. This assumption marked a dramatic departure from classical physics. It implied that energy behaved less like a flowing liquid and more like a collection of indivisible coins. One could not pay half a coin, only whole units were allowed. At first glance, this idea seemed artificial, even absurd. Planck himself did not believe that energy was fundamentally granular. He viewed the assumption as a formal device, a temporary measure to rescue the equations. Yet the results were undeniable. When Planck applied this assumption, the equations matched experimental data perfectly across all frequencies. The ultraviolet catastrophe vanished. The mathematical expression produced finite, realistic energy distributions that aligned exactly with observation. For the first time, theory and experiment were in complete agreement. The success of this approach forced physicists to confront an uncomfortable truth. The quantization of energy was not a mathematical trick. It described how nature actually behaved. Although Planck initially resisted this interpretation, the implications became impossible to ignore. The assumption worked because it reflected a deeper structure of reality. What made this idea especially revolutionary was its subtlety. There was no dramatic announcement, no declaration that classical physics was wrong. Planck presented his findings cautiously, emphasizing the empirical accuracy of the formula rather than its philosophical implications. The scientific community received the work with interest, but not alarm. Few immediately grasped how radical the underlying assumption truly was. Energy quantization quietly undermined the foundation of classical physics. If energy could only change in discrete amounts, then continuity, one of the core principles of classical theory, was no longer universal. The smooth curves of classical equations could no longer describe all physical processes. Nature, at its most fundamental level, operated in steps rather than flows. This idea challenged not only physics, but human intuition. Continuous change felt natural because it mirrored human perception. Quantized change, by contrast, seemed mechanical and unnatural. It suggested that reality itself was constructed from indivisible actions, each governed by fixed rules. This vision of nature was profoundly different from the classical world. The resistance to this idea was subtle but persistent. Many physicists accepted Planck's formula while ignoring its deeper meaning. They treated quantization as a convenient assumption rather than a physical truth. Others believed that a future classical explanation would eventually eliminate the need for discrete energy units. Few were willing to accept that continuity itself had limits. Despite this hesitation, the idea of energy quantization began to spread. It provided a new lens through which unresolved problems could be examined. Phenomena that had once seemed mysterious now appeared structured and rule-bound. Spectral lines, atomic stability, and radiation patterns all hinted at an underlying quantized framework. Planck's reluctance to embrace the full implications of his idea highlights the depth of its impact. Revolutions in science are often imagined as bold challenges led by rebellious figures. In reality, some of the most transformative ideas emerge quietly, introduced by individuals who are themselves uneasy with change. Planck did not seek to overturn classical physics. He revealed its limits by following evidence with intellectual honesty. The quantization of energy represented a new kind of scientific reasoning. It suggested that mathematical success could point toward physical truth even when intuition resisted. This shift placed empirical accuracy above philosophical comfort. Nature, not human expectation, became the final authority. As the implications of quantization gradually became clear, the scientific community began to recognize its significance. Energy was no longer an abstract, infinitely divisible quantity. It possessed a fundamental scale defined by a constant that would later bear Planck's name. This constant set the boundary between the classical and the quantum worlds, marking the point where old assumptions failed. The introduction of energy quantization did not immediately dismantle classical physics. Instead, it revealed that classical laws were approximations, valid only when energy changes were large compared to the quantum scale. In everyday life, these discrete steps were too small to notice, giving the illusion of continuity. At microscopic scales, however, quantization dominated behavior. This realization transformed the scientific understanding of reality. It suggested that the universe was built upon limits, thresholds, and minimum actions. Nothing could be infinitely small or infinitely smooth. There was a grain to existence itself, invisible to the senses but essential to its structure. The true power of Planck's idea lay not in its immediate acceptance, but in its capacity to generate new questions. If energy was quantized, what about matter? What about momentum, angular momentum, and light itself? These questions would soon drive the next generation of physicists to explore deeper and stranger territory. The second keynote of Planck's revolution, the introduction of energy quantization, was thus not a single moment of insight, but a gradual shift in thinking. It marked the transition from a universe governed by continuous certainty to one defined by discrete possibility. This shift would eventually reshape physics, technology, and philosophy in ways that Planck himself could scarcely imagine. In this quiet departure from classical assumptions, the foundations of modern physics were laid. Without dramatic language or bold predictions, a simple mathematical assumption revealed a universe fundamentally different from the one humans had believed they understood. Energy, once thought to flow endlessly, was now understood to move in steps, and with that realization, the door to the quantum world opened. As the idea of energy quantization began to circulate quietly within the scientific community, its implications slowly grew more difficult to ignore. What initially appeared as a narrow solution to a specific radiation problem began to illuminate patterns across multiple areas of physics. Phenomena that had resisted explanation under classical assumptions now appeared connected by a common principle. The universe, once imagined as infinitely smooth, revealed signs of an underlying structure that operated according to strict and subtle rules. One of the most striking consequences of energy quantization was its ability to explain the precise regularity observed in atomic spectra. When atoms emitted light, they did not produce a continuous range of colors, but distinct lines at specific frequencies. Classical physics offered no convincing reason for this behavior. Electrons, imagined as orbiting charges, should have been capable of emitting radiation across a wide spectrum. Yet experiments showed otherwise. The introduction of quantized energy levels transformed this mystery into an ordered process. Atoms could change their energy only in fixed steps, and each step corresponded to a specific frequency of light. This insight marked a profound shift in how matter itself was understood. Energy was no longer a passive property that objects possessed in arbitrary amounts. It became an active constraint, shaping how systems evolved and interacted. The discrete nature of energy exchanges imposed order on processes that once appeared chaotic. Stability, once inexplicable, now emerged as a natural consequence of quantized rules. The scientific response to this shift was cautious. Many physicists adopted the mathematical framework while postponing judgment about its physical meaning. Quantization was treated as a useful abstraction rather than a literal description of nature. This hesitation reflected the depth of the conceptual change required. Accepting quantization meant acknowledging that classical intuition had limits, and that nature did not always conform to continuous reasoning. Despite this resistance, the predictive power of the idea could not be denied. Each successful application strengthened its credibility. When Albert Einstein applied the concept of quantized energy to light itself, proposing that electromagnetic radiation could behave as discrete particles, the implications expanded even further. Light, long regarded as the perfect example of a wave phenomenon, now exhibited particle-like behavior under certain conditions. This extension of Planck's idea revealed that quantization was not an isolated feature, but a universal principle. The growing influence of energy quantization forced physicists to rethink the meaning of measurement and observation. If energy could change only in discrete amounts, then physical processes were governed by probabilities rather than certainties. One could predict which transitions were allowed, but not always when they would occur. This probabilistic character marked a departure from deterministic ideals that had dominated science for centuries. Planck himself observed these developments with a mixture of pride and discomfort. While his work had opened the door to a new understanding, he struggled to accept the philosophical consequences. The abandonment of strict determinism challenged deeply held beliefs about causality and order. Yet even as he resisted some interpretations, the foundation he had laid proved unshakable. As experimental techniques improved, evidence for quantization accumulated. Phenomena such as specific heat, anomalies in solids, and the photoelectric effect displayed behavior that could only be explained through discrete energy exchanges. Each confirmation narrowed the space for alternative explanations. The quantum hypothesis evolved from a tentative assumption into a central pillar of modern physics. The transition from classical continuity to quantum discreteness also altered the language of science. Concepts such as orbit, trajectory, and path lost their classical meaning at microscopic scales. Instead, physicists described systems in terms of states, transitions, and allowed values. This new vocabulary reflected a deeper conceptual transformation, one that reshaped not only equations, but the very questions scientists asked. Energy quantization also redefined the relationship between mathematics and physical reality. Previously, equations were seen as representations of continuous processes unfolding in space and time. The quantum framework suggested that mathematics could reveal structures beyond direct sensory experience. Abstract symbols described rules governing unseen actions, actions that nevertheless determined the behavior of the physical world. As the 20th century progressed, the implications of quantization extended beyond pure theory into practical technology. Devices that relied on controlled energy transitions became possible only because energy was quantized. Lasers, transistors, and atomic clocks all depended on precise, discrete energy levels. What began as an abstract solution to a radiation problem became the foundation of modern electronics and communication. This technological impact highlighted an important lesson about scientific revolutions. Their value is not always immediately apparent. Planck could not have foreseen the practical consequences of his idea, just as 19th-century physicists could not imagine quantum computing. The true power of energy quantization lay in its ability to reveal a deeper layer of reality, one that future generations would learn to harness. The philosophical implications were equally profound. Quantization challenged the notion of a fully predictable universe. If energy changes occurred in discrete jumps governed by probability, then absolute certainty was no longer attainable. This realization did not diminish the power of science, but redefined it. Understanding became a matter of statistical laws rather than exact predictions. The acceptance of this new perspective required a cultural shift within physics. Authority gave way to evidence, and tradition yielded to experiment. Younger scientists, less bound by classical expectations, embraced the new framework with enthusiasm. Older generations adapted more slowly, but the consistency of results left little room for doubt. Energy quantization also revealed the layered nature of physical laws. Classical physics did not disappear. It emerged as an approximation valid under specific conditions. When energy scales were large and quantum steps were negligible, continuity reappeared. This coexistence of frameworks demonstrated that scientific truth is contextual rather than absolute. In this sense, Planck's contribution represented not a rejection of the past, but an expansion of understanding. He showed that nature could not be fully captured by a single set of assumptions. Instead, reality revealed different aspects depending on the scale at which it was examined. This insight became a guiding principle of modern science. The second keynote of the quantum revolution thus unfolded gradually, through accumulation rather than confrontation. Energy quantization reshaped physics not by dramatic upheaval, but by persistent success. Each experiment that confirmed discrete behavior reinforced the conclusion that the universe operated according to rules deeper than classical intuition allowed. By accepting quantization, physics entered a new phase of maturity. It acknowledged the limits of human perception and embraced mathematical abstraction as a tool for discovery. The universe, once imagined as smooth and predictable, emerged as structured, probabilistic, and profoundly subtle. This shift did more than solve existing problems. It redefined what it meant to understand nature. Knowledge was no longer measured solely by certainty, but by coherence, consistency, and predictive power. The quiet acceptance of energy quantization marked the moment when physics learned to listen more carefully to nature than to itself. In the end, the idea that energy comes in discrete units transformed more than equations. It changed humanity's relationship with the universe. It revealed that reality is not obligated to align with intuition, and that progress often begins with ideas that feel uncomfortable. Through a single reluctant assumption, Max Planck opened a doorway into the quantum world, a world that continues to challenge, inspire, and redefine our understanding of existence. The introduction of the Planck constant marked a quiet but decisive turning point in the history of science. At first glance, it appeared to be nothing more than a small numerical factor inserted into an equation to make experimental data agree with theory. Yet this modest constant carried implications that extended far beyond its original purpose. It established a fundamental limit in nature and permanently altered how scientists understood energy, motion, and reality itself. Before the Planck constant entered physics, there was no recognized minimum scale for physical action. Energy could be divided endlessly, time could be reduced indefinitely, and physical processes were assumed to unfold smoothly without interruption. The universe, according to classical thinking, had no built-in granularity. The Planck constant shattered this assumption by introducing a fixed scale that could not be crossed or ignored. It defined the smallest meaningful unit of action in the physical world. What made this constant so revolutionary was not its size, but its universality. The same value appeared regardless of the system being studied. Whether dealing with radiation, atoms, or later subatomic particles, the constant imposed the same constraint. This suggested that quantization was not a special feature of certain materials or conditions, but a fundamental property of nature itself. The universe, it seemed, was governed by a built-in rule that limited how finely physical quantities could be divided. At first, many physicists underestimated the importance of this constant. They treated it as a mathematical convenience rather than a window into reality. Its numerical value was extremely small, making its effects invisible in everyday experience. Because classical physics continued to work well at large scales, the constant appeared irrelevant outside specialized experiments. Yet this invisibility was precisely what made it so profound. It explained why the classical world appeared continuous while the microscopic world did not. As the significance of the Planck constant became clearer, it forced a reassessment of long-standing assumptions. Determinism, once regarded as an unbreakable principle, came under pressure. If physical processes were constrained by a minimum unit of action, then outcomes could no longer be predicted with absolute certainty. Instead, probabilities entered the heart of physical law. The constant did not merely modify equations, it redefined what equations could claim to represent. The Planck constant also reshaped the relationship between measurement and reality. It implied that observation itself was limited by fundamental constraints. One could not simultaneously measure certain quantities with unlimited precision because the constant set a boundary on what nature allowed. This insight transformed measurement from a passive act into an active interaction with the physical world. Observers were no longer detached recorders of reality, but participants within it. Perhaps most importantly, the Planck constant unified a growing collection of unexplained phenomena under a single conceptual framework. Atomic spectra, thermal radiation, and later quantum transitions all obeyed rules dictated by this constant. What once appeared as isolated mysteries became expressions of the same underlying principle. The constant acted as a bridge, connecting diverse areas of physics into a coherent whole. The presence of this constant also redefined the meaning of simplicity in science. Classical physics prized smoothness and continuity as signs of elegance. The Planck constant suggested a different kind of elegance, one rooted in limits and discreteness. Nature was not less orderly for being quantized, it was more structured. The constant revealed that complexity could arise from strict constraints rather than from unrestricted freedom. Over time, the Planck constant became a symbol of the quantum world itself. It marked the boundary between classical intuition and quantum reality. Whenever physical systems approached scales where this constant could not be ignored, classical descriptions failed and quantum behavior emerged. This realization gave physicists a powerful tool for understanding where and why old theories broke down. The change in scientific thinking brought about by the Planck constant was subtle but permanent. It taught physicists that the universe operates according to rules that may defy intuition yet remain mathematically precise. It demonstrated that even the smallest numerical value could carry enormous conceptual weight. Through this single constant, nature declared that there are limits to continuity, limits to certainty, and limits to classical imagination. In this way, the birth of the Planck constant did more than solve a technical problem. It reshaped the philosophy of science, introduced humility into human inquiry, and revealed a universe governed by deep, unyielding principles. What began as a reluctant adjustment became one of the most powerful ideas ever introduced into physics, quietly guiding humanity toward a deeper understanding of reality. The most remarkable aspect of Max Planck's contribution to physics is that he did not set out to create a new theory of nature. His work was focused on solving a specific technical problem, and yet it unintentionally ignited a revolution that reshaped science forever. This quiet beginning is what makes the emergence of quantum theory so extraordinary. It was not born from bold declarations or radical manifestos, but from careful reasoning and reluctant acceptance of evidence. When Planck introduced the idea of energy quantization, he believed it to be a temporary assumption, a mathematical device necessary to make equations fit experimental data. He did not imagine that it described a fundamental feature of reality. In fact, Planck spent years hoping that a deeper classical explanation would eventually replace it. This hesitation reveals how deeply rooted classical thinking was, even in the mind of the man who opened the door to its transformation. Despite Planck's caution, his idea proved impossible to contain. Other physicists quickly realized that quantization could explain problems that had resisted classical solutions for decades. Albert Einstein extended the concept to light itself, suggesting that electromagnetic radiation could behave as discrete particles. This interpretation challenged long-held beliefs about the wave nature of light, and introduced a duality that would become central to quantum theory. What Planck had viewed as a technical fix now appeared to be a universal principle. As the implications spread, a new generation of physicists began to explore the strange consequences of quantization. Atoms were no longer seen as miniature solar systems governed by classical orbits, but as systems constrained by allowed energy states. Transitions between these states occurred in sudden jumps rather than smooth motion. This view explained atomic stability and spectral lines with unprecedented accuracy, reinforcing the reality of the quantum world. The development of quantum theory was not a single event, but a gradual process built upon Planck's original insight. Each contribution expanded the framework while preserving the core idea that energy exchanges are discrete. What made this process unique was its collaborative nature. Different scientists approached the problem from different angles, yet all found themselves guided by the same foundational assumption. Planck's reluctant hypothesis became the common thread connecting their discoveries. One of the most profound consequences of this development was the abandonment of strict determinism. Classical physics had promised a universe in which the future could be predicted exactly if the present were known. Quantum theory replaced this certainty with probability. Outcomes could be calculated statistically, but individual events remained unpredictable. This shift represented a fundamental change in how science understood causality and control. Planck observed this transformation with mixed emotions. He recognized the success of quantum theory, yet struggled with its philosophical implications. The idea that nature was governed by probabilities rather than certainties conflicted with his belief in an orderly universe. His discomfort highlights an important truth about scientific progress. The originators of revolutionary ideas do not always embrace their full consequences. Understanding often advances faster than acceptance. The unintentional nature of Planck's revolution underscores the power of intellectual honesty. By following evidence rather than ideology, he allowed reality to guide theory, even when the results were uncomfortable. This commitment to truth over tradition became a defining feature of modern physics. It demonstrated that scientific revolutions do not require rebellion, only integrity. Over time, quantum theory proved its worth not only in explaining natural phenomena, but in shaping modern technology. Devices that rely on quantum principles now form the backbone of contemporary life. From electronics to medical imaging, the consequences of Planck's quiet insight extend far beyond the laboratory. What began as a hesitant adjustment to a radiation problem now influences how humanity communicates, computes, and explores the universe. The launch of quantum theory also changed the culture of science. It encouraged openness to counterintuitive ideas and fostered a willingness to question even the most trusted assumptions. Physicists learned that elegance and truth are not always aligned with intuition. Sometimes, the universe reveals itself through rules that feel strange but prove consistent and reliable. In retrospect, the unintended birth of quantum theory stands as one of the greatest examples of how progress emerges from uncertainty. Planck did not seek to redefine reality, yet his work revealed that reality was far more subtle than classical physics had imagined. The revolution he sparked was silent, gradual, and deeply transformative. Through this quiet shift, physics entered a new era. The world was no longer a predictable machine, but a dynamic system governed by probabilities and limits. That transformation began not with ambition, but with a single assumption made in the face of stubborn evidence. In allowing that assumption to stand, Max Planck unknowingly changed the course of science forever. One of the most striking features of Max Planck's contribution to science is the way his ideas challenged classical physics without direct confrontation. Unlike many revolutions that arrive with loud opposition and clear breaks from the past, Planck's work moved quietly, almost respectfully, through established traditions. He did not reject classical physics outright, nor did he seek to dismantle its principles. Instead, he revealed its limitations by extending its logic to a point where it could no longer hold. Planck's approach was deeply conservative by nature. He believed in the power of established laws and trusted the mathematical structure of classical theory. His goal was always reconciliation rather than replacement. When faced with experimental data that contradicted classical predictions, he did not declare those theories wrong. Instead, he searched for a bridge that could connect observation with tradition. This mindset allowed his work to be taken seriously by a community that might otherwise have resisted radical change. The challenge Planck posed to classical physics was subtle but profound. By introducing quantized energy, he left the core structure of classical theory intact while quietly inserting a boundary it could not cross. Classical equations still worked, but only within certain limits. Beyond those limits, new rules applied. This shift reframed classical physics not as false, but as incomplete. It was a powerful redefinition that preserved past achievements while opening space for new understanding. This respectful challenge made the transition to quantum theory less violent than earlier scientific revolutions. There was no immediate rejection of Newtonian mechanics or Maxwell's equations. Instead, these laws continued to function where they were valid. The idea that a theory could be both correct and limited represented a new way of thinking about scientific truth. Knowledge became layered rather than absolute. Planck's reluctance to overstate his conclusions played a key role in this process. He presented his findings cautiously, emphasizing empirical accuracy rather than philosophical implications. This restraint encouraged acceptance rather than resistance. Many physicists initially adopted his formula without fully engaging with its deeper meaning. Only gradually did the revolutionary implications become clear. As evidence accumulated, classical physics began to appear less like a universal framework and more like a special case. Its assumptions of continuity and determinism remained powerful tools at large scales, but failed at the microscopic level. This realization did not diminish the value of classical theory. It clarified its domain of application. Such clarity strengthened science by preventing overreach and encouraging precision. The manner in which Planck challenged classical physics also influenced the culture of scientific debate. It demonstrated that progress does not require hostility toward existing ideas. Respectful extension, grounded in evidence, can be equally transformative. By working within the system, Planck allowed the system to evolve naturally rather than collapse under pressure. This approach also highlighted the role of humility in scientific advancement. Planck did not assume that human intuition was a reliable guide to nature. When intuition conflicted with data, he chose to trust the data. This humility opened the door to concepts that felt uncomfortable but proved necessary. It reinforced the idea that science advances not through certainty, but through willingness to revise belief. Over time, the quiet challenge Planck introduced reshaped the foundations of physics. It encouraged scientists to look beyond smooth curves and continuous motion, toward a world defined by limits and discrete events. Yet this transformation occurred without discarding the mathematical elegance of classical theory. Instead, elegance was redefined to include constraint as well as freedom. The influence of this shift extended far beyond Planck's original problem. It changed how physicists approached unexplained phenomena, how they interpreted experimental results, and how they evaluated the scope of their theories. The idea that every model has a domain of validity became a guiding principle of modern science. In this way, Planck's work stands as an example of how deep change can occur without confrontation. By challenging classical physics from within, he preserved its strengths while exposing its boundaries. This method of transformation proved more enduring than outright rebellion, allowing old and new ideas to coexist and inform one another. The fifth keynote of Planck's legacy lies in this quiet balance between respect and revision. His work showed that the most powerful revolutions are not always those that destroy the past, but those that reveal its limits. Through careful reasoning and intellectual honesty, Max Planck demonstrated that science progresses not by rejecting tradition, but by understanding where it ends and where new insight must begin. The influence of Max Planck's ideas did not remain confined to theoretical discussions or academic debates. Over time, the principles that emerged from his work reshaped technology, industry, and everyday life in ways that few could have predicted. What began as an abstract attempt to understand radiation evolved into a foundation upon which much of modern science and technology now stands. This transformation illustrates how deeply theoretical discoveries can alter the practical world. As quantum ideas matured, they provided explanations for the behavior of matter and energy at the smallest scales. These explanations, once purely conceptual, soon became tools for innovation. Understanding how electrons occupy discrete energy levels made it possible to manipulate materials with unprecedented precision. The properties of solids, once treated as bulk phenomena, were now understood as the collective behavior of countless quantum systems. One of the earliest technological consequences of quantum theory was the development of semiconductors. Classical physics could not fully explain why certain materials conducted electricity under specific conditions while acting as insulators under others. Quantum principles revealed that electrical conductivity depended on quantized energy bands within materials. This insight enabled the design of transistors, devices that could control the flow of electrical current with extraordinary efficiency. Transistors became the building blocks of modern electronics, transforming communication, computation, and information storage. The impact extended further with the invention of the laser. The ability to produce a coherent, focused beam of light depended on precise control of energy transitions within atoms. Such control was only possible through quantum understanding. Lasers, once theoretical curiosities, became indispensable tools in medicine, industry, and science. From surgical procedures to fiber optic communication, their applications reshaped modern society. Quantum theory also revolutionized measurement and timekeeping. Atomic clocks, which rely on exact energy transitions within atoms, provide time measurements of unparalleled accuracy. These clocks form the backbone of global navigation systems, telecommunications, and scientific research. The reliability of modern infrastructure depends on principles that trace directly back to Planck's original insight. In medicine, quantum-based technologies enabled new ways to see inside the human body. Imaging techniques rely on interactions between radiation and matter that classical physics could not adequately describe. Quantum understanding made it possible to interpret these interactions accurately, leading to safer and more effective diagnostic tools. The ability to visualize internal structures without invasive procedures transformed healthcare. Beyond technology, Planck's revolution reshaped scientific disciplines far beyond physics. Chemistry was redefined through quantum explanations of bonding and molecular structure. Materials science emerged as a field capable of designing substances with tailored properties. Even biology began to incorporate quantum concepts to explain processes at the molecular level. The reach of quantum theory demonstrated that Planck's work had implications wherever matter and energy interact. Perhaps most striking is how seamlessly these technologies integrated into everyday life. Smartphones, computers, medical devices, and communication networks operate using principles once considered abstract and counterintuitive. The quantum world, invisible and unfamiliar, now underpins the most familiar tools of modern existence. This quiet integration reflects the power of foundational science to shape society without drawing attention to its origins. The broader impact of this transformation lies in how it changed humanity's relationship with knowledge. Planck's work showed that understanding the universe at its deepest levels could yield practical benefits far beyond immediate expectations. It encouraged sustained investment in fundamental research, even when applications were not obvious. The technologies that define the modern era emerged not from targeted engineering alone, but from curiosity-driven exploration. The sixth keynote of Planck's legacy is thus the enduring connection between theory and application. His ideas demonstrated that the most abstract questions about nature could lead to concrete advances that improve lives. This connection reinforced the value of scientific inquiry as a long-term investment in human progress. In recognizing this legacy, one sees that Planck's silent revolution did more than change equations. It changed the trajectory of civilization. By revealing the quantum structure of reality, his work provided the tools to shape a technological world unimaginable to earlier generations. The devices and systems that surround us today stand as living evidence that even the quietest scientific insights can echo through history, reshaping how humanity lives, works, and understands its place in the universe. The legacy of Max Planck's work is not confined to a single theory, a constant, or a mathematical formula. Its most profound impact lies in the enduring way it continues to shape our understanding of the universe. The silent revolution he initiated more than a century ago has never ceased to influence scientific thought, technological development, and philosophical reflection. Even today, the principles he uncovered guide research, innovation, and exploration in ways that would have been unimaginable in his own time. Planck's discovery that energy is quantized revealed a universe structured by limits and discrete actions, a stark contrast to the continuous, predictable world of classical physics. This realization was only the beginning. As scientists explored the consequences, they discovered that these discrete units govern phenomena across the natural world. The structure of atoms, the behavior of light, the interactions of subatomic particles, all became understandable within a framework that Planck had inadvertently created. The universality of quantization became a guiding principle for future discoveries, providing a consistent thread through otherwise disparate phenomena. Quantum theory, which arose from Planck's work, has continued to evolve, yielding insights into realms that were previously unimaginable. It has given rise to quantum mechanics, quantum electrodynamics, and more recently, quantum information science. Each development builds upon the principle that energy, matter, and information are governed by fundamental constraints. Planck's initial insight into discrete energy exchanges now informs the study of particles that exist fleetingly, fields that permeate space, and interactions that underpin the fabric of reality. Itself, the influence of this revolution extends beyond the laboratory. Technology, industry, medicine, and communication systems all depend on quantum principles. Modern electronics, computing devices, lasers, and imaging technologies trace their functionality to the same insights Planck introduced over a century ago. These applications are not incidental. They are direct consequences of the quantum rules he helped uncover. Humanity's ability to manipulate and harness nature at its smallest scales is a living testament to the enduring relevance of his ideas. Moreover, Planck's legacy has transformed how scientists think about the universe. The shift from determinism to probabilistic models redefined the nature of prediction, measurement, and certainty. Where classical physics offered neat predictability, quantum theory emphasizes the limits of knowledge and the inherent uncertainty of processes at microscopic scales. This philosophical shift has profound implications, influencing everything from the methods of scientific inquiry to broader questions about reality, causality, and the role of observation. Planck's work also continues to inspire new generations of scientists. His method, careful observation, rigorous mathematics, and intellectual honesty serves as a model for approaching problems that resist conventional solutions. It demonstrates the importance of curiosity, perseverance, and willingness to follow evidence, even when it challenges deeply held beliefs. The silent, gradual nature of his revolution is a lesson in humility and patience, showing that transformative discoveries do not always announce themselves loudly, but unfold quietly through careful reasoning and persistent inquiry. The broader impact of Planck's ideas is evident in the way modern physics approaches fundamental questions. Researchers exploring black holes, quantum entanglement, and particle physics continue to operate within the framework his insights made possible. Without the foundation he established, understanding the quantum nature of the universe would remain inaccessible. His work created a lens through which the subatomic world, the structure of matter, and even the early moments of the cosmos can be examined with precision. Finally, Planck's silent revolution underscores a timeless truth, that even the smallest, most abstract ideas can change the world forever. His initial hypothesis, made out of a need to solve a technical problem, has cascaded through generations of science and technology, influencing every aspect of modern life. The principle that energy is quantized and the framework it enabled continue to inform the way we explore, understand, and interact with reality itself. In this way, Max Planck's work is not merely a chapter in the history of physics. It is an ongoing story that shapes the present and will guide humanity's understanding of the universe for centuries to come.